Hello, this is Professor Rogelio Caballero from Academia San Jose de Cupertino. Today we're going to discuss how to complete the square, okay? So when students learn completing the square, they tend to focus on the procedure, the how to go through the motions, okay? This naturally causes a lot of confusion because if we don't know why we're doing something, it is much more difficult to learn how to do it, okay? So in this video, we're going to discuss first why and when it's necessary to complete the square, and then we're going to have a look at some examples, okay? So let's first discuss when it's not necessary to complete the square. That's when we're in the presence of a perfect square trinomial like this one, okay? X squared plus 2px plus p squared, okay? So how do we recognize them? How do we recognize perfect square trinomials, okay? If we have two terms, such as x squared and p squared, and the third term is twice the product of the square roots of those two terms, then that's a perfect square trinomial. We should all know that from middle school, okay? So we also know how to factor them, okay? So this is equal to x plus p squared, okay? Very good. A particular example of a PST could be this one, okay? X squared plus 2x plus 1, okay? Whose factorization is x plus 1 squared, okay? Very good. So a quick comment. What is the advantage of the factored out expression x plus 1 squared over the original trinomial? Okay. The advantage is that in the factored out expression, there is only one instance of the variable x, whereas there are two instances of the variable x in the original expression, okay? That difference may sound trivial, but as we're going to see in our next video, it is actually very, very important for solving certain kinds of integrals of topic 6.10 of AP Calculus AB and AP Calculus BC, okay? So very good. So these are perfect square trinomials. For the sake of brevity, let's call them PSTs. And we're not going to use completing the square for them, okay? Since they are perfect, there is nothing to complete there, okay? So when is completing the square necessary, okay? Completing the square is necessary when we have a trinomial that is not a perfect square, such as this one, okay? X squared plus 2x plus 2, okay? So very important, this is not a PST, okay? This is not a PST. How do we know that? Okay, well, we know that because we have this term, x squared, so far that's a perfect square. We have 2, okay? But the third term is not twice the product of the square roots of x squared and 2, okay? We don't see a square root of 2 here, so that already tells us that this is not a perfect square trinomial, okay? So, however, we would like to somehow put this non-perfect square trinomial into a form where there is only one instance of the variable x, okay? As we said, that's one of the objectives that we are pursuing here, okay? And one way we can achieve that is by observing that these two trinomials are very similar, okay? Have a look at these two trinomials. They are very, very similar. We have these two terms are exactly the same, okay? The difference is in the third term, okay? So what we can do here is that we can say, okay, so this is not a PST, but it's almost a PST, okay? So let's work a little bit with that last term to see what we can do with that, okay? So let's write this as x squared plus 2x, and let's split these two into 1 plus 1. Okay, very good. So what do we have now? Now we have a PST, okay? Now we have a PST plus an extra thing, okay? So let's factor that PST and we get x plus 1 squared plus 1, okay? And that's it. We have achieved what we wanted to do, okay? We wanted an expression where there was only one instance of the variable x, okay? In contrast with the original expression where there are two instances of the variable x, okay? When we do that, when we get this non-perfect perfect square trinomial into this structure, okay, the square of a binomial plus something extra, we can say that we have successfully completed the square. Okay, very good. So that's it. So let's apply this principle to other examples. Okay, very good. So let's see this other example that we have here. Okay, so let's see x squared plus 4x plus 5. Okay, so what's going on here? What's going on in this example? Well, the first important observation is that this is not a PST. Okay, this is not a PST, so that's calling for completing the square. Okay, so since we want to bring this into a form that is as close as possible to a PST, let's do something. Let's write over here, let's write a PST, which is going to be our model. Okay, so let's write x squared plus 2px plus p squared. Okay, this is going to be our model, what we're after. Okay, so very good. So now let's compare these two expressions. Okay, we have this x squared, which corresponds to this other term. Okay, we have that this second term 2px should correspond to this 4x. Okay, and by comparing these two terms, okay, we're going to try to find out what's the value of p, okay, that transforms these two terms into a perfect square trinomial. Okay, obviously that value of p, it's going to be such that 2p, it's going to be such that 2p, this coefficient right here, it's going to equal 4. Okay, and of course that gives us that p equals 4 halves, which is simply 2. Okay, very good. So that's the value of p that it's going to transform these two terms, x squared and 4x, okay, into a PST. So what we're going to do now is that we're going to write that this trinomial is equal to x squared plus 4x, okay? And I'm going to add something here, okay? I'm going to add p squared, okay? Which we know that p squared, in this case, is simply 2 squared, okay? So let's add that 2 squared, okay? And as you can see, we already have here the perfect square trinomial that we were after, okay? However, we have some other stuff to do. We also have a term here, plus 5, and we can add this 2 squared out of nowhere, okay? If we add that 2 squared out of nowhere, okay, then this trinomial, it's not going to equal the expression that I'm writing here, okay? So very good. So what I'm going to do now is that I'm going to subtract that 2 squared in order that these two expressions be equal, okay? That they be the same, okay? Very good. So as we said, we already have here a PST, so let's factor it out, okay? So that's going to be x plus 2 squared, okay? And we have here minus 2 squared, don't forget about that, plus our independent term, okay? Very good. Now let's add these two terms that are outside our parentheses, and we get x plus 2 squared minus 2 squared, that's minus 4 plus 5, that's 1. Okay, and that's it. This This is our final result. Okay, we have succeeded in completing this, in completing the square. How do we know that? Because we're left with this, a binomial squared, okay, plus or minus one term. Okay, very good. So that's the objective of completing the square, as we said earlier. Okay, very good. And as you can see, we have here in this final expression only one instance of the variable x, whereas we have two instances of the variable x in the original expression. Okay, very good. So yes, okay, we have succeeded in completing the square. Okay, so very good, very good. So let's see another example. Let's see another example. Let's see another example. Now we're going to have this trinomial. Okay, so we have x squared plus 3x plus 3x plus 5. Okay, again, this is not a perfect square trinomial. Okay, how do we know that? Well, because we have this term, x squared, and we have this other term, 5, but this middle term is not twice the product of the square roots of x squared and 5. Okay, there is no square root of 5 there, so this is not a perfect square trinomial. Okay, so that calls for completing the square. Okay, that's what we are going to do now. Okay, very good. So as we said, completing the square is partly trying to transform this into a form that resembles as closely as possible a perfect square trinomial. Okay, so what I'm going to write here is my model. Okay, x squared plus 2px plus p squared. Okay, and what I'm going to do now is to find out what's the value of p that turns these two terms into a perfect square if I add p squared, okay, for that particular value of p, okay? So obviously from comparing this 2p, okay, with this 3, okay, we can see that 2p has to equal 3, right? 2p equals 3, from where we get that p equals 3 halves, okay? 3 halves, very good. Okay, so what am I going to do now? Now I'm going to write x squared plus 3x, okay? And then I'm going to add my p squared, okay? P squared. So we have plus 3 over 2 squared. And that's the perfect square trinomial that I was after, okay? Unfortunately, that's not the end of it because we have one extra term, okay? And again, we cannot add these 3 halves squared out of nowhere, okay? We need to subtract them, okay? In order that there be equality between these two expressions, okay? Very good. So, so what am I going to do now? Now I'm going to take my PST, the 3 terms that constitute my PST, and I'm going to factorize them, okay? So we have x plus 3 over 2 squared, and then we have minus 3 over 2 squared plus 5, okay? Very good. So what am I going to do now? Now I'm going to add the 2 extra terms outside my parentheses, okay? So that's going to be x plus 3 halves squared, and you can check that minus 3 halves squared plus 5, that's 11 fourths, okay? And that's it, okay? That's the expression that I was trying to achieve, okay? This is my final result. I have successfully completed the square, Okay. So one last remark, okay? Just look how ugly the final answer is, okay? And that's because we have these two fractions, 3 over 2 and 11 fourths, okay? Which in turn are the result of dividing this coefficient 3, which is an odd number, by 2. Okay, so don't be alarmed if that happens. Okay, if you end up with a final result like this, okay, with a bunch of ugly fractions, okay, that's fine, because what we're after is this, a result that it's a binomial, x plus 3 halves squared, okay, a binomial squared, plus some term, okay. That's what we're after, okay. Don't worry about the fractions. And why are we pursuing that? Well, because we need an expression where there is only one instance of the variable x, okay? And in our next video, we're going to see how to apply completing the square to solving certain kinds of integrals where that's going to become extremely relevant, having only one instance of the variable x, okay? So thank you for watching this video, and I hope it's been useful to you.